Hi there, nice to see you. This is lesson 3, so by now I know you've already filled in your table of contents, updated it with today's lesson title. I know that your lesson page is ready to go and we're ready to take notes. So I'm just going to jump right into it. However, if you're not ready yet, go ahead and press pause and we'll get back into the lesson. Today we're going to talk about equivalent ratios. Now this lesson is broken up into 2 parts, where we're going to talk about equivalent ratios to solve problems. And in the next one, we're going to bring some triangles into it. Being able to determine how ratios and equivalent ratios help us solve problems with similar triangles is very important in 6th grade math, so we'll definitely spend some time with that. You'll also notice that underneath those 2 videos, there are 2 exercise documents for you to practice everything that we do in these 2 videos. Okay? And finally, the exercise review video that I do will actually cover both of those exercise documents in the same video. So that's kind of a breakdown of how this whole lesson will work. Okay? First, let's talk about equivalent ratios. Okay? This is very important. We already kind of covered a little bit about this. We've talked about how to change a ratio into a different looking ratio, but has the same relationship. Okay? You've already done an exercise about cookies, I believe. We've already done an exercise about how do I make my little singing choir into a bigger singing choir. And let's look a little bit deeper into that whole concept. I'm going to start with this ratio, which is 2 to 3. It could be 2 to 3 of anything. I haven't given it any labels yet. And that's because I really just want to talk about the numbers for a minute. Okay? Now, if I were to say, can you tell me a ratio that's equivalent to 2 to 3? You think you could do that? Here's an interesting thing about math. There are infinitely many equivalent ratios to 2 to 3. In other words, they just keep going and going and going. As long as the relationship stays the same, it really doesn't matter what the values are on top. Now, how do I keep that relationship the same? Well, we've already practiced that a couple times, like I said. We just have to make sure that we are doing the same thing to the top that we are to the bottom. So I could start off really easy. I could say, well, an equivalent ratio to that is, or a ratio that's equivalent to 2 to 3, I could just multiply by 2. Let's double it. Okay. So if I decide I want to multiply the top by 2, that means I have to do the same thing to the bottom. So 2 times 2 on top, 3 times 2 on the bottom. I'm multiplying the exact same number, and that's going to give me 2 times 2 is 4, 3 times 2 is 6. Now I have 2 equivalent ratios. Okay? If I get those little multiplication things out of the way, I can see it a little bit clearer. 2 to 3 and 4 to 6 are equivalent ratios. That means the value is totally the same. The relationship is totally the same, just because the numbers changed a little bit, okay? But the relationship is still the same. There's a word for this. Yes, we're going to call them equivalent ratios, and you'll see them called that over and over and over again. But when you have 2 ratios that are equivalent to each other, but don't share the exact same quantities, we call this a proportion. Two equivalent ratios with different quantities is a proportion. Okay? So they have the same relationship, they just have different quantities. And when you have this set up right here, you can say that this ratio is proportional to this ratio. That'll become a little bit more important later on. Okay? So a proportion is what we call this setup of 2 equivalent ratios, and this ratio is proportional to this ratio. Make a note of that in your journal, because this is going to be an important vocabulary word later on, and we're going to spend some more time with it as we go through this lesson. Okay? So, I mentioned before that there are infinitely many equivalent ratios to 2 to 3. All I have to do is pick a different factor. I could pick 7. If I multiply 2 by 7, have to do the same thing to this. So another equivalent ratio of 2 to 3 would be 2 times 7 is 14, 3 times 7 is 21, 2 to 3 and 14 to 21 are equivalent ratios. This is another example of a proportion. Okay, so that's the first thing that's kind of important to realize, that if you ever want to write an equivalent ratio to the one that you're given, just make sure you multiply both the top and the bottom by the same factor. And you can't go wrong, as long as your multiplication is correct. Okay? All right. Now I have a question. I'm going to write a ratio 1 to 4. Let's keep it simple so that we don't confuse ourselves. And I'm going to ask this question. Is 1 to 4 equivalent to 3 to 12? Are these equivalent ratios? Is this a proportion? Sometimes you'll see a problem like this written with a little question mark on top because they want to know, is this actually true? There's a couple of ways we can test this. Okay? The first thing we can do is ask ourselves, is the same thing happening to this number to get this number as what's happening to this number to get that number? All right? Now we're going from 1 to 3. That means we're getting bigger. So we're not dividing, we're definitely multiplying. What do you multiply by 1 to get 3? 1 times 3 is 3. Okay? So that's multiplication by 3 happening there. If I multiply the bottom number by that same factor, do I get 12? Yeah. So right away I can see by doing this little test right here that this is a true statement. 1 to 4 is indeed equivalent to 3 to 12. Or another way of saying it is 1 to 4 is indeed proportional to 3 to 12. Okay? But there's another test we can do too. And it's probably the one I used to do the most. Because sometimes numbers get weird, or sometimes numbers get really big, and you don't want to try to figure out what the factor is. So here's another thing you can do. It's called cross multiply. If you see this equal sign in the middle, you know it's a proportion, and you know you can do this test. We're going to do cross multiply. Okay? So we're going to look across the equal sign. 1 is diagonal to 12. And we're going to go diagonal this way as well. 4 is diagonal to 3. And all we're going to do is multiply those diagonals. So starting up here, 1 times 12 equals 12. And if we go this diagonal, 4 times 3 is 12. If you have a match, if these two numbers are the same, then you know you have a proportion. They call that the means and extremes test. Okay? So there's two different ways right there that you can figure out if your two ratios are equivalent, if they have the same relationship but different quantities. Okay? Let's try one more. Let's go with another simple one, but not as simple. Let's have a ratio of 5 to 3. And again, that could be anything. That could be 5 mints to 3 M&Ms. Okay, it doesn't matter. I want to know, is this ratio proportional to 15 over 10? Is this a proportional relationship? Are these equivalent ratios? Okay? Now remember, there's two tests here. The first one says, let me figure out what you have to multiply the top and the bottom to get this top and bottom. Easy enough. What do you multiply by 5 to get 15? 3, right? So I have to do that. If that works, then I have to do that to the bottom number as well. So 3 times 3, ooh, does that equal 10? No, that doesn't. 3 times 3 is 9. So we're a little bit off, okay? This test right here shows us that we don't have an equivalent ratio set up. We don't have a proportion, all right? So let's just to be safe, let's try one more test. Let's try the cross multiplication and see how this is working out. Let's go diagonal from 5 to 10. 5 times 10 is 50. 3 times 15, 15, 30, 45. And here again, we can see that this is not a match. Those numbers have to be exactly the same for this to show a proportional relationship, and it doesn't because these numbers don't match. So our factor test didn't work, and our cross multiplying test didn't work. This right here is not a proportion. These two ratios are not proportional. If I went from here to here, something went wrong, okay? The relationship that was happening here broke down and became a different relationship here. That's very important, okay? So let's try one more thing. Try a little bit of a thought experiment here. When I was in, I'm going to say 3rd grade, even though it probably happened in 4th or 5th grade too, and Valentine's Day rolled around at my school, I always wanted to give Valentine's Day, we were supposed to give Valentine's cards to our classmates. So, one time I was asking my teacher, because I lost my paper that had everybody's names on it, I said, how many girls and boys are here in this classroom? And she wouldn't answer me. She gave me a test. She said, by the way, this story is totally made up, but it makes the point. She said, well, the ratio of boys to girls in this classroom is 3 to 2. And when she said that, remember she said boys to girls, so that means that boys were up here and girls were down here. So there was a ratio of boys to girls of 3 to 2. And I said, well, okay, that doesn't really help me. She said, oh, and by the way, there are 20 students in this class. Okay, so this is vital information, but she wasn't going to tell me how many boys or how many girls there were, so I had to figure this out on my own. Now, right away you can tell the story's not true because I said 4th grade, and this is not 4th grade math. But let's just keep going with the story, and we'll be able to figure this out. I need to know how many boys there are in my class and how many girls there are in my class, because I'm not going to give a boy a Valentine card that was meant for a girl, at least not in my world. But so here we go. I know the ratio and I know how many students are in my class. Okay? From here, I should be able to figure out how many boys and how many girls there are. So let's think about this. 20 total students, and here's my ratio of boys to girls. I can set up a proportion here. Let's try this. Can I set it up like this? Can I just put 20 students right here? Does that work? Not quite, right? Because here on this part, on this ratio, the bottom number is the number of girls in the class. But over here, the bottom number is everybody. And we already know that that's not a match, because here we have a part-to-part ratio, and over here we're automatically seeing that we're going to have a part-to-whole ratio. So we're going to have to change something. I don't know how many girls are in my class. I don't know that. I just don't know. Okay? So let me set up another proportion down here. And instead of using girls, I'm going to use boys and girls in this new ratio that I write down here. So my new ratio is going to be read boys to everybody. Boys to, and what's this number right here going to be? Well, I'll just add these two up. Boys and girls, right? 3 plus 2 is 5. So now I have a part-to-part ratio here that I'm going to hold on to because it's information that I need. And here I have a part-to-whole ratio. I have boys to everybody. My proportion is going to have two equivalent ratios here. Boys to everybody, and over here, boys, which I don't know yet, to everybody. See where we're going with this? I'm going to put a little, I don't know, right here, because I don't know how many boys there are yet. But I'm going to find that out. Later on in this course, we'll start using variables here, like x or something like that. But for now, we'll just say, I don't know. So let's figure this out. How do I find that missing number? Well, I think the easiest way that I can think of is to say, okay, well, what did I do down here? What happened in the bottom to go from 5 to 20? I went from 5 to 20, so I went from a smaller to a bigger number, which means I multiplied something, right? What do you multiply by 5 to get 20? 4. Is that what you got? 5 times 4 equals 20. And as we've been saying so many times in these past couple lessons, whatever you do to one part of your ratio, you must do to the other part. Okay, so if I multiply 4 by everybody, I have to multiply 4 by the boys also. 5 times 4 is 20. 3 times 4 is 12. So instead of this little question mark, now I know that there are 12 boys out of 20 total students. That helps. Now I know I need to buy 12 boys Valentine's cards. Which only leaves me one more question. How many girls? How many girls Valentine's cards do I need to buy? Okay? And that I can easily find from this ratio. If I know there's 20 total students and 12 boys, then all I have is a nice, simple subtraction problem. 20 minus 12. So when I go buy my Valentine's cards, I need to make sure that I get those numbers. But we're not done. I do want to make sure that you're caught up with me right now. So if you need to, go ahead and pause the video because I'm going to erase a lot of this. And we're going to check to make sure that our answer is correct, to make sure that it makes sense. So click pause if you need to. Okay, so we know that we had 12 boys in the class and 8 girls. Our original ratio that our teacher gave us to try to figure all this out was 3 to 2. The question we need to ask ourselves is this a proportion? If it is, then we know our answer is right. All that work that we just did was good for something because if this ratio is proportional to this ratio, we know that we did it all right and we're going to go buy the correct amount of Valentine's cards. Okay? So, 2 different ways. One, what do you have to do to 3 to get 12? Multiply by 4, right? So 3 times 4 is 12. So that you have to do that to the bottom number as well. 2 times 4 is 8. Good. So far, it looks great. Okay, so let's try the other test. Let's try the cross multiplication test. Let's look at the top here and the bottom here. 3 times 8 is 24. And then let's do the same thing. Bottom, cross multiply with 12. 2 times 12 is 24. This number and this number are the same, so we know we did this right. We know that we're dealing with 2 equivalent ratios, and now we know how many of each of those Valentines we need to go buy. Gotcha, teacher. Okay, that's the end of this lesson. Next one you're going to watch, we're going to bring some triangles into the mix. Now, this is assuming that sometime in your previous education you were familiar or at least exposed to the words congruent and similar. And if that's not the case, don't sweat it, because that's the first thing we're going to talk about is what is a congruent triangle and what's a similar triangle, and how can we use these to actually figure out things that are almost impossible to figure out. All right? Can't wait to see you there.